Go to the screen. Okay, let me start. Okay, 19 join. What about remaining? 5 missing. Quickly join. Let me start, because we have given enough time already.
Share the link in the chat.
Yeah, I will chat. Conversion. Conversion. Langsung. Clubhouse yang all leading. Brian. Olive. Olive pada dia tak. No. Give you full name and then practice. Olive start playing. More. More. Lazy Anjing, join please. For present Omar, take a more minutes. Olive is leading now. Chapter 1 Omar 0. Omar, Michael Ryan of Ryan writing. What remaining? What was the question? Can you talk? The purpose is only. Only 16 fully done. I stop. But 100% timing over, getting over. 3 more. Take it like shall we end the game? You can check your answer, please. Supposed to be 5 minutes. We have 10 more minutes. Okay, let me end here. You can continue. If you have any questions in the quizzes, you can ask. Lucia, Wangwa, Khalif for today. So you have to get more winners every class. Let me see the first 10 people also there. First 10 in the class for this quiz. Khalif, Wang Waisen, Chaujia, Ivan, Martin, I don't know who is what. Tonka, Lamzo, Muhammad Anas, Michael Ryan. Michael Ryan, no? He was not doing it, suddenly coming to 10th place. Must come to all pick up the for front ground, not background, background. Okay, I stop here. We will continue with our class on strain, how to calculate the strain. We saw the stress-strain relationship, which is material property, right? Material property with which we can say when the material is going to fail, right? We did start with, there are 3 types of deformation: tensile, compressive, and shear. We have taken only tensile last time. We conducted tensile test and found out how much is the value of strain, right? Value of strain through the graphical representation, right? We learned some theory on that, how to calculate the where are the regions, right? What are the regions? What are the profile that it can yield? In any tensile test, meaning what? A member which is subjected to a tensile force. Tensile force means it's a pulling force. It has different regions like this, right? One is elastic, this is yielding, this is strain hardening. We are going to see one by one now. This is totally negging, about to fail. Negging is a dangerous zone or between ultimate and fracture. You have to take action immediately in this region, okay? My cursor, you can see my cursor, right? Okay. I take the laser pointer. Okay. This region is a very dangerous zone, or the engineer in charge in the company, if it is a tools and machines, engineer in charge should start, the material is still working but started negging, right? Started going to fail. And this is a region you have to take action. The time given for taking action to replace or stop the work, right? To avoid any dangerous failure or hazardous at the end, right? So We note the critical status of the strength of specification, proportional limit, elastic limit, yield stress, ultimate stress, and fracture stress, right? In the elastic region, you can see that there is a clear proportion, right? As long as the strain is increasing, as long as you increase the load, the strain is increasing. All of you know what is strain, isn't it? It's a deformation, failure, failure of the member due to the loading, external loading, right? When the strength of the member is low compared to the external loading, it tend to fail, right? And it can take up the load until its strength, until its ultimate strength. What is the mild steel strength? Last time we did some graph, right? Some values. What is the strength of mild steel? 200 and 200 to 250, okay? 200 and 200 to 250 megapascals. Please remember this. Some of the numbers you should remember in your mind, like not referring to tables and codes always. See here, megapascals. Somewhere here, mild steel. Somewhere here, 200 to 250, yeah? And the hardest one is graphite. It can go up to how much? Giga, right? Almost giga. How much giga? Say 100, 100 gigapascal. It's already megapascal. 100,000 megapascal is 100 gigapascal already. 100 gigapascal graphite. So you can compare the difference between the mild steel, the usual one, the copper. Copper is very low, right? The strength of the copper is very low. The ultimate strength of the copper is very low compared to mild steel. With copper is just 80, it can be 70 to 80 and so on. Remember these points. In this case, the graph is plotted and we are understanding the different regions here. At this point, it can regain, although the loading is then, the strain rate in proportion means it's still working. It can come back to original position, right? Although it is extended, it can come back to original position. That is the meaning of elasticity, right? If you pull the rubber band and just leave the force, it will come back to original position, right? Similar action is taking place in this region. That is why we call this as a mode of resilience or bearable limit, or material compatibility is good at this region. After this, even after you stop, see there is no load increasing, load, it means the load is removed, load is stopped, there is no more loading applied, but started increasing in strain rate, isn't it? Increasing in strain rate, giving you different crucial points like yielding point, right, or the region between the elastic and plastic, and then ultimate stress, and then fracture. Do you understand this? In this case, yielding point, it started yielding from changing from elastic to plastic. In this case, this is totally a plastic region, right? From this point until this is plastic region. But the plastic also there is a variation due to good tensile strength of the member. It has some yielding, some strain hardening, and then only necking started. All these responses are in the longitudinal direction. And this one, the other direction, which is cross section, also in response to yielding, in response to the load applied. That's why it is important that you should know what is the tensile strength, ultimate strength of the member that you have chosen for your design, and the property of the material governs. So every material is tested and before use for construction or for manufacturing, assembling, right? Now, any question at this point? I show you a very quick video to understand and remember how this kind of negging is taking place. Can you see this video? One moment, I share this video for you. A quick one to remember how this is taking place. I think this is the tensile test. Yeah, come on. So when you plot between stress and strain for a member, white color is the member, a rod fixed at both ends, and the application of load is in away from the center, right? It is being pulled at the ends by an axial load, uniaxial load. Uniaxial is referring to all the loads are on the same plane, right? One plane, right? Did I start it? Yeah, started. See, I said control, right? Here is the playback speed. You can have a control. Later I show you. You click on the playback speed. I put very low so that you can observe the variation. See, it's still It's still the member is nothing happening. It's very good, very good. And it just started yielding in the vertical direction only. Started in the vertical direction only. If you go to this region, it's still loading. It's a very good phenomenon. The load is applied. It can bear the load. It is still within the strength of the material. And see there, slowly, slowly. And see here, negging started. When it crosses this point, right? When it crosses this point, when it crosses this point, you can see the bend here, small bend here, right? Because it's going to reach the ultimate. It's going to reach the ultimate. The yielding started. It is going to reach the ultimate. That's why the negging started at this point. I take the. Hope you can see my cursor moving. Negging started. I see the negging. Negging started growing in this dimension. In addition to the elongation, the negging is also happening at one point. Broken already. Breaking point. Reach the breaking point. This is how they test the materials, whatever it may be. Maybe they come out with an innovative material. They still have to undergo a tensile stress like this by pulling at the ends, applying the load, and then you can plot it. Come on, let's understand from this um, different regions. Again, you have to know and apply in your calculations. Where is it? Come on, the slides. So in all, we have to know what is the value of the strain rate, what is the, there is another value we are introducing here, which is called elastic, modulus of elasticity, right? Modulus of elasticity. You see there is a region wherein there is a proportionality, right? There is a proportionality between stress and strain, right? And this region is subjected to or following what you call Hooke's law. Hooke stated that there is a proportion between strain and the stress, and this region is controlled by, called as, or governed by Hooke's law, which says strain is proportional to stress or vice versa. Accordingly, you can write like this. Mm, who come out with the equation saying that stress is proportional to strain, and he replaces this proportionality by a constant called E, modulus of elasticity, right? Is a number, and this is a rate, and this is the megapascal or pascal, right? You can see the graph plotted for different material. People have tested a different material and plot, come out with their own graphs, and then composition of all the graphs, integration of all the graphs gives you the values of different material. And this region is modulus of toughness, right? As we told, after this, right, we put a vertical line. After this is fully of toughness area. It will give you how strong the material is. Next is a strain energy. You should also know what is strain energy. As the material is deformed by an external load, the load will do external work, which in turn will be stored in material as internal energy. This energy is related to the strain in the material, and so it is referred to as strain energy. If you treat the strain as a deformation or a rate, it is in percentage, right? You can also change it in terms of how much work done, right? Because this kind of pulling and this kind of deformation doing some work, right? Sometimes it may be necessary to cut the material, right? You have to cut the material, you have to assemble the material, you have to customize the member. In all, there is some job done, right? In that case, you have to calculate how much is the energy required, how much is the deformation energy required to get particular shape or get particular bending or the junction. In that case, this formula will be helpful to say it is denoted by U, which is half times, it is just from half mv square. I don't go into derivation of all these things, but kinematics is all related to movements and forces, right? In schools, in what you call grades, upper grade or lower grade, you would have studied potential energy, kinetic energy, right? Kinetic energy is given by half mv squared. Based on this, they derive this formula. I'm not going to derive it, but understand that it is related to this formation, mass into acceleration or mass into velocity square, mass into velocity square. Based on this principle, they come out with the energy calculation for objects which is moving, and the equation. Yes.
What is the E?
E is the modulus of elasticity. Just now we say modulus of elasticity. We will study about this in a while. Elasticity. Just now I introduced here modulus of elasticity. Okay, given by Hooke's. Okay, there's a law and there's replaced with a coefficient called modulus of elasticity, which is saying E is equal to, you can write one more equation also, then you understand even better. Like this, E is equal to ratio of stress over strain, right? Following Hooke's law. So this is modulus of elasticity, is a number, okay? It's a coefficient, it's a number, which will help you to decide type of material, whether how much the elasticity value of the material, how far it's the yielding, I mean when it's going to reach the yielding point and so on, right? Okay. This formula I'm not going to derive. As we will be providing the equation, but this is based on the kinematics of materials, okay? And then another region modulus of, based on this equation, right, where you have the resilience, the elasticity zone, where the material is showing a elastic property. Elastic property means, see, when you apply the load, it will get extend, right? When you apply, like this, it's easier for me to show. When you apply the load, it will get extended to, when you apply load, it will get extended to this region, right? When you release the load, right, when you release, when you release the load, it will come back to its original position. That is called elasticity, right? This type of behavior is observed from here to here. From this point to, from this region to this, okay? And also the loading condition from here to here. Once the load is removed, the action of, once it reaches the yielding point, from there the plastic region started, or it is a transition between elastic to plastic, right? Actually yielding point exactly starts from here, yielding, the material going to yield, material going to fail, start failing, right? Modulus of resilience is the area under this curve, right? The area, because the number is only the stress. So when you multiply, get the area under this, where whatever the points under this one, if you design a member for this point, this point, this point, any point under this curve will be showing a modulus of resilience, or the member is good for up to its yielding point. It can bear the load, right? And then it represents the largest amount of internal strain energy per unit volume of the material can absorb without causing any permanent damage to the material. Is still, this region is very good, it still accept, that means it can come back to original, right? Even it is yielded, it may be a hard material, mild steel, wrought iron, plastic, the polymer or of any type. It can go a little bit extension, but once the load is removed, it can come back to original. So there is no permanent yielding occurring, and thus the energy calculated from this is giving you the strain energy processed by the body, or otherwise called as modulus of resilience. Another region after this, what happened? After this is total hardening. Let's see how is strain hardening take place. When yielding has started, right? This point, upper limit, lower limit we call upper limit, lower limit. I'm sorry, this is lower, right? This is lower, this is upper limit. Or there's a transition between yielding elastic and plastic, or yielding point. When yielding has ended, a further load can be applied to the specimen, resulting in a curve that raises continuously but becomes flatter until it reaches the maximum stress, referred to as ultimate stress. The raise in the curve is called strain hardening, right? Okay, strain hardening means, see, there is at this point, until this point we are loading, right? After this point there is no loading, the loading is removed, right? And so the curve is trying to flatter, right? The curve is trying to flatter. It is a little bit increasing, right? It is a little bit increasing because of the material property, right? But it has not shown any type of elastic property, right? It is increasing in strain, means what? It is elongated, it is subject to fail. If there is no fail or somewhere here, right? If the value is still here, even after you increase the load or just slowly removing, this point is slowly removing the load, okay? That is why it is still having a strain rate, slowly removing the load. If it is not increasing, if this line is not growing, then it is called perfect. But it is growing for no increase or very little bit increase of loading until it reaches a point called ultimate strength. So this total region is called a plastic region, and this is a point up to which the material can withstand even with some deformation, some plastic deformation or plastic behavior of the material shown until this only up to and until ultimate strength, right? After this, right, after this means what? There is a strain, a constant strain. We can say the flatten, it is flattened or the strain is constant, right? No, the stress is removed, but the strain is constantly increasing, constantly increasing, right? Constantly increasing until it reaches the, actually the this cover, it is differing from material to material. If you see the actual curve, it is still like this. It's a bit, little bit higher. Original curve will be little bit higher. Means what? Due to material property, it is still higher. But because you are using testing equipments, you have a kind of a curving in nature. Okay, but supposed to be a flat, or it's a constant value with no load applied, but the strain rate is increasing in this direction until it reaches the ultimate strength, which is the total strength of the member, or we decide that is the capacity of the member. From that point onwards, the failure started. The name of the failure is called negging. A kind of a negging started, reduction in the cross section until it fractured. Okay. How brittle material will behave? Where is the brittle region? And how plastic will behave? What is strain hardening? The answers here, but all these answers are taken from these definitions. Okay. Can you how brittle material will behave? There are two types, right? Ductile and brittle material. Hmm. How brittle material will behave? How ductile? Mild steel is ductile or brittle material? Number one. Then you can answer my question. Take mild steel. Is it a ductile material or brittle material? What's the meaning of ductile? It can be elongated, right? Can be made into rods and bars or of different section, right? Malleability, ductility, all you studied in schools, right? The capacity or ability of the material to, tendency of the material to become flattened or extended so that it can be made into different shapes and designs for our purpose, right? Different purposes. But brittle, immediately, even you cannot extend, right? It will immediately break, right? When you try to pull, it will break like plastic. It will immediately break. Concrete immediately break, right? It is not a ductile material. Immediately it will break, but has a compressive strength, but not a tensile strength. It will brittle, right? So now, just now we saw the mild steel behavior, right? This is fully behavior of the mild steel, right? Then you have to differentiate between mild steel and brittle, I mean ductile material and mild steel, sorry, brittle material. How plastic will behave? These are other questions against. This is all for mild steel and ductile material, right? The other way is the brittle material, plastic material, and if you want, you can show here. They will be in this region, right? This region, meaning there will not be, for plastic it will be very quick, it will be reaching very quick. Here there is a good triangle obtained for a ductile material, right? For plastic it will be very quick, and you will have a more plastic region than the elastic region for brittle materials. I will show a little bit difference later on. Let me complete this one. What is strain hardening? Strain hardening, right? That is also important to recall. um, there is no, although the load is removed, the answer is like this. Although you remove the load, you're not loading at all, right? You're not loading at all, but still the specimen tend to fail because of increase in strain. The increase in strain is called strain hardening, right? Simple what I explained to you. At this point, either the load is stopped or slowly removed, but still the strain is keep increasing, right? It is due to the internal action or The material is unable to withstand the load, so it yields. Yield means it tend to fail. That is called strain hardening. So like that you explain with a graph if asked. Further topics on stress strain. Determine the elastic deformation of axially loaded member. Apply the principle of superposition for total effect of different loading cases. Deal with compatibility conditions. Use force method for analysis. Right. We'll see one by one. These are the 4 types of problems accordingly, right? You will have these stress strain calculations based on only for elastic deformation, another one with superposition of 2-3 loads. Although it is uniaxial, 2-3 loads will be given. Then deal with compatibility condition. You are asked to find out what is the material property, what is the strength of the member. That is called compatibility conditions. And then force method. Force method of analysis we will do in this, not in detail in this chapter, but in 4th chapter we will do this one, force method of analysis. All of you remember at this point, we are talking about how the member behaves for the external loading, right? Until you finish this chapter, you please keep away your thinking about force and moments. It is not relevant here, okay? We are talking about how the member yields, what is the deformation, what is the difference in shape and also in cross section, isn't it? So we are talking about the material internal properties, either cross section or length or shape. What happened to the cross section, whether the increasing or decreasing. If increasing, it is a compression. If decreasing, it is a tension. And what happened to the length? If the length is increasing, it's a tension. If the length is reducing, it's a compression type of force. And then what happened to the shape? If the shape is changed, square to a rhombus, rectangle to another parallelogram, and so on, when the shape, when there is a failure at an angle, right, then it is called shear. So you are talking about deformation or displacement or deflection. I cannot use the word deflection, although you're going to study it in detail later on. Better not to use deflection. It's a deformation, right? Changes happening to the internal body due to internal forces developed in the body. That is what you have to remember. Just forget about the external forces and calculating exact force moments and so on for a while. Otherwise, you get confused the terms. I want to show this one, shear strain. Let me show the video later on. Let us cover this some portion. Strength parameter. Okay, you are going to learn another parameter or modulus. Shear modulus of elasticity or modulus of rigidity. Same goes to the same way we can define it. Shear stress is defined by your tau, right? Tau represents the shear stress. When sigma represents the, remember those notations, please remember it. We denote the normal stress by sigma and the shear stress by tau, okay? Like we define for the ratio between stress and strain in normal stress, we can also define the shear stress with the strain. If I denote the shear stress by tau and the strain, corresponding strain by gamma, and the ratio between them, right? We say according to this value is given by Poisson, so we call this as Poisson's formula, Poisson's equation. Tau is proportion to gamma. To remove proportionality, introduce a constant which will have all the rest of the properties that are ignored or not used in this relation. We denote by G. By that you have an equation called tau is equal to G times gamma, where G is known as radius of gyration, or where is it? I don't know whether it's written here. Later on, but for now you use it as modulus of rigidity. Okay, last time you studied E, right? E as modulus of elasticity, G as modulus of shear modulus or modulus of what is the shear modulus of elasticity or the modulus of rigidity? It's confusing one moment. Shear modulus, let it be shear modulus, but there is no stick with a very small angle and deviation is very small. So shear modulus or the modulus of rigidity. Okay. Don't use any other terms, just use whatever the term I'm using here. Sometimes in the textbook they confuse, they use it in a different way. Just follow the one text which I'm writing here. I'm following one text and the corresponding terms. So G is known as modulus of rigidity. Let's see how it is. This one initially it is square, right? Because of the tangential shear acting on it, it will tend to bend in this direction, making an angle, right? Making an angle. If it is to the horizontal like this, it depends on which direction you want to, which plane you want to calculate, whether it's XY plane or YZ plane or XZ plane and so on, right? G is related to the modulus of elasticity. Okay, the relation between this one also we have to derive, but for now we just take it for understanding purpose. The relation between modulus of rigidity and modulus of elasticity. Okay, this is due to tensile strength of the body. This is due to shearing strength of the body. The relation between these two is given by what is called Poisson ratio. We'll study what is Poisson ratio. Poisson ratio also giving you how the cross section behave. What is the deformation in the cross section? With that, we can derive the equation between G and E, which is G is equal to E over 1 plus 2 times 1 plus nu. It is nu, Poisson ratio. Let us see what is Poisson ratio. Poisson ratio, lateral deformation. It compares the lateral and longitudinal deformation at the cross section. Gamma, what is called nu, not gamma, sorry, nu. Nu is equal to sigma lateral over sigma longitudinal. So in the video I've shown, you have seen the member is elongating in the lateral longitudinal direction and also in the lateral direction, isn't it? This is longitudinal, this is lateral, right? Lateral and longitudinal. Along the length, along the cross section. There are two types of deformation in any member, right? Poisson ratio defines how much it is going to fail between these two. The ratio is between strain in the lateral direction over strain in the longitudinal direction. Both are negative because there is a change, right? Elongation also we take it as a, although it is additional, but it is a negative value, so we take it as negative. So dW, this is the width or the cross section, the lateral dimension. This is the longitudinal dimension. End up with the equation called the equation for Poisson's ratio. Actually this is positive longitudinal, I need to remove it. We take the one moment, we take the this eraser. I'm not taking eraser. Anyway, I will explain the next. See the lateral dimensions, it's a cross section, right? Cross section is reducing, so it's negative. Longitudinal, it is extending. Extension is taken as positive, compression is taken as negative, right? Reduction is taken as negative. In tensile, it is extending, that is positive. So this is positive, this is negative, end up with negative value. Okay, that is what given here. You can read it from the theory. So Poisson ratio decides the overall deformation, right? Last time Young's modulus gives you how much is the elongation coefficient for the elongation, and your shear, the one modulus of rigidity or what do you call modulus of shear, gives you how much is sheared. But this one gives you both cross section and also lengthwise. And then creep. This is another type of failure. Creep, fatigue. I think fatigue also I cover here. Yep. Creep. We are talking about how the material behaves for the external loading. One is the elongation and its coefficients, corresponding coefficients. Next one is the creep. What is creep? Different types of material behave different way. Please remember this point. What is happening here? You have the, in the same graph we can plot it between the load, right? The stress and the number of, okay, this is most important in mechanical people only, right? Where the wheel is always in rotation, the turbine is always in rotation, the car, the gearbox always in rotation, right? And there are some gap interval, right? Today morning it's running until afternoon and then stop. Again morning they start. Intermittent running, right? Intermittent running, or it is running for a continued interval, some number of cycles running for a certain interval, right? With some gaps in between. So there's a chance of material material freezing thawing, or otherwise extension again go back, right? If the material is subjected to loading within the elastic limit, it has to elongate and then go back, elongate, go back, right? For certain period of time and then stops overall, again restart. That means the deformation is quite often. The member is facing the deformation quite often or repeatedly. That is important, the word repeated. I think it is here. I don't know. Let me read the paragraph. When the material is repeatedly loaded for a certain duration of time, it will tend to uh, subject to what is called creep. I read from here. Time dependent permanent deformation is known as creep. Normally, creep is considered when metals and ceramics are used for structural members or mechanical parts that are subject to high temperature. Yeah, another effect is temperature effect. When it is running for long, you have to account for temperature effects as well. For some materials, however, such as polymer and composite materials, including wood or concrete, temperature is not an important factor. And yet, creep can occur strictly from long-term load application, right? This is number of cycles. How many number of cycles? See, then as the number of cycles keep increasing, right? SN curve. It's called SN curve. Very famous curve for mechanical engineers to design their components. They have to design how much is, where is the creep and where is the fatigue value, where is the strain hardening, strain energy. All these values they have to calculate before they choose the member. So when you plot between the value S, right, the what do you call the stress value on the corresponding number of times that is it is occurring, right? Number of times it's occurring. For example, you take the steel value, it is starting here, right? Starting here. We start from here. Very high, right? And initially it is very high, and then slowly reducing, right? Slowly reducing as the number of cycle is increasing. The stress value or stress produced or developed in the body is slowly reducing and stopped once for all for a prolonged time. See here, the stress produced or resisting power of the body is stopped at about ninth cycle. 9 into 10 power 6 number of times of rotation, it stopped, and then continuously the stress produced by the body is constant, or it cannot do any number of cycles, right? It cannot do any number of, there is a chance that if you load it, if you repeatedly use it or keep on increasing, there's a chance that it will fail at one point, right? Because there is no fluctuation, it can maintain a constant value due to prolonged running, 10, 100, 500, 1000, right? And then when you come to aluminum, it has a good value started, right? Value started with, and then increase reducing to a very low value than the steel member, and then started creep, just creep or maintain a constant value, then response or regain its original position. Just maintain. It's all happening between ultimate and breaking point. Okay, that you have to remember. It's all reaching, right? Already at this point it's already reached yielding point, started yielding, and then maintain a constant until it breaks. At one point it will break. So engineers have to know at which point it is going to break, at what number of cycle it is going to break after this, reaching this yield or overcome this elastic limit, and how long, what is the duration and number of cycles that it is prolonged or maintaining constant. So this has to be studied well by the engineers before you design the member. Another type, okay, it's a colorful diagram for you. Stress range, in take it as a megapascal, and this side is cycles, number of cycles, right? In other words, tolerance limit, endurance limit is given. You see here a very high limit, stress it can take. You imagine you apply this much stress and you're running for 1,000 cycles, keep increasing 10,000 cycle, right? The stress value produced is low, getting reduced. The body unable to resist. Ferrous material, maybe the mild or raw ion. The stress produced by the body is keep reducing and reaching a limit at 10 power 8. Let it be 7, it's 100,000, right? More than that. So it stops somewhere here, 1 million, 10 million, 10 million stops somewhere here, cycles, stops already, and then maintain a constant creep, just creep, about to harden, or what do you call the creep, reach already the maximum ultimate strength and then hardening. And this limit is called as, so you can take this as a endurance limit, right? A complete level of endurance limit. If you design beyond this, right, there is a risk because the stress is reducing. Stress is completely reducing. The number of cycles increasing, the stress is completely reducing. But this limit is the safest limit, right? This limit you cannot load beyond this. If you run the machine with this load, you can run this cycle, this cycle, this cycle, this cycle until this, and up to the limit of breaking. But if you increase, there is a certain limit at which the creep started, you cannot load anymore. Okay. Then another type of Fasson curve. Yeah, example. This example is very interesting to see how the creep is. I mean, how they fix a failure, right? How they fix a failure. Okay. Take any point. Take any point on this curve, right? What is this point? X value is 10 per 1 cycle per minute, right? 1 cycle per minute. 1 year. Oh yeah, you can determine how many years, right? By this number of cycles and that corresponding load, you can calculate the number of years it can withstand. Number of service period, right? That's why they say your service is after 6 months, after this, right? How they calculate by means of this calculation SN curve. You can say when it is requiring, when it is requiring to replace the component or servicing, right? This one point which determines the stress value is 100 megapascals, right? 100 megapascals or 15 case, say 100 megapascals can lose or can run 500 cycles, right? When you apply 100 megapascals, the number of cycles that it can go is about 10,000. How much is it? Roughly 8. If you divide into 10, it may be somewhat 8. Let it be not even 8, 7. 7 times 7 times 10 power 5 is the limit number of cycles it can go for, right? And then the calculation value says 5,000 cycles to fail. 5,000 cycles to fail means what? In 1 year, in 1 year, it is in 1 year, every cycle, right? It will have 1 cycle per minute. If it is running for 1 cycle per minute, chances of failure will be 500,000. Chances of failure will be 500,000. If you want, I will do the calculation and show you so that you can understand these numbers written here, right? I repeat, if you take any loading at any point, you can say how long this is going to sustain, or what point the particular component going to fail. That can be determined by this SN curve. Taking any load and then relate to the number of cycles, calculate the rate per minute, right? You calculate the rate per minute, then you'll get the time. I did a calculation somewhere to make you understand. One moment. Didn't bring it. Okay, I will work out some calculation on this so that you can understand how they determine the period of failure, right? This helps you to determine a simple calculation only. Wait, let me think a minute. 500,000 cycles per minute. Yeah. They take this as 5. 1, 2, 3, 4, 5. Yeah, 5,000. This is 5,000, 500,000 cycles already, right? Yep. Hmm. Per minute, 1 year failure. 365. Yep. Do you get the meaning from the graph? The loading, right? With the loading at 100 megapascals, it can run for 500,000, right? 500,000 cycles it can make, right? So per minute, if you would calculate roughly, like it's a rough calculation, I cannot say 1 cycle per minute, even less than that, because the number is very high, isn't it? How many minutes in a year? Come on, based on that you can calculate. How many minutes in a year? Quickly calculate and tell me. How many minutes in a year? By to multiply lang. 365 by 60 by 60 by 60. How much minutes?
525,600.
Divide that one, you will get per minute. How much is it? It says one roughly la. Maybe it's a higher value. 1 cycle per minute it can make. So you decide how much is the failure point. Either way, either you can determine this given this, or given this you can determine this one. So that's how this have graph is helping. These are all mechanical guys have to bother about all this fatigue, creep and fatigue. I repeat, fatigue is like this. At one point it started making a constant value, right? There is no change in the load. There is no change in the load, but the strain is maintaining a constant. On the other hand, fatigue is total failure. Fatigue is worse than creep. Creep, at least you have a constant value. Here, I read the sentence here. Where is it? When a material, what is it? Metal. I cannot see this one. Subjected to a body, body subjected to repeated cycles of stress or strain. You know what is stress or strain, right? Stress is the response of the body to the external force. Strain is the deformation due to the external force. It causes its structure to break down, ultimately leading to fracture, right? Always remember that curve. It was elastic, getting back, and then started yielding a crack like, and then not even a crack like, internal crack I can say, and then slowly reaching ultimate, started breaking. That is our curve. But in the curve, these are the peculiar things for other materials. I don't bring all the materials, but when you compare to other materials, civil engineer, mechanical engineer, any engineers, we have to deal with different types of materials, right? And they behave in a different way. That is why you have to know more factors than just strain, stress and strain. And these factors are important for mechanical engineer. Only machine parts, metal parts, all metals, right? Non-metals also subjected to this type if you do it, but metals are the best example with which mechanical engineers and process engineers are working on. They will come across these problems. This big, okay, come on, let's read what is this. Ultimately leading to fracture. The behavior is called fatigue. Yep. So after creep, the stage is after creep, it will be broken, right? Broken is the condition that after which is put on use, and these are usually responsible for large percentage of failure in connecting rods, crankshaft. Yeah, crankshaft. Once you saw the negging, you must replace. Otherwise, at one point, it is going to fail. Fatigue, stop working. Fatigue means stop working. Steam engines, turbines, blades, connections, supports for bridges. It's mainly wear and tear, you see. The very good example is your brake shoe. Daily you're using car, right? The brake shoe is there and it is attached with the your wheel, right? The wheel which is rotating. Always you press the brake, right? Every time you press the brake, it gets a wear and tear. At one point, it fails to get it grip, right? When you press the brake, it lost the limit of coming closer to the brake point or closer to the wheel. It stopped braking or fracture occurred. And then materials. So there's a type. These are the type of failure which is occurring for different materials at different points. One moment. I will bring the video if you want, how the ductile and what do you call the one. The difference between ductile and brittle materials I show in the video, then you understand better. Why by term I am unable to explain totally. I will bring the video in a while or in the next class. Okay, let's follow with this one. Modulus of elasticity is a measure of linear relationship between stress and strain. The common unit is, what is the unit of modulus of elasticity? We define this as, you substitute then, we call coefficient. You substitute the units, you will get it. What is the unit? We write it as E is equal to stress over strain, ratio between stress and strain. What is the unit of stress? Megapascal, right? Megapascal. And strain is a percentage or number or anything. So we end up with the unit of the stress itself, or unit of the type of stress that is developed. So all the units of stress is equal to the unit of the modulus of elasticity. Remember this point. Any question at this definition? I repeat, modulus of elasticity is defined as ratio between stress and strain. When you substitute the unit, stress is denoted by megapascal or kilonewton per meter square or newton per meter square over the percentage or number. Strain is a number, ratio between two linear dimensions, right? Changing length to original. So I end up with the unit, just the unit of the stress itself. All this as a coefficient, we already divide by the percentage. That's why we take it as a coefficient or number. Come on, Poisson ratio is common engineering material, lies in the range of, yeah, this is important. Huh? What is Poisson ratio? Lateral to longitudinal. Remember this equation? Lateral to longitudinal, the ratio between deformation in the lateral dimension to the longitudinal dimension, which defines your material design. Okay, you cannot design the member just with the strain or stress, strain value. You have to see the both deformation in both direction, which is called Poisson ratio. Poisson ratio is the one that help you to design the member. So you remember this equation, then answer this question. The ratio between lateral to longitudinal should be which range? You think can answer me? No answer? No answer. You take the ratio and substitute and see. Oh, 6:30, half an hour only left, of God. Okay, you give me the answer next class. Let me do this calculation now. One calculation on strain energy, strain and calculation of strain. One moment, I quickly open this file. Let me unshare this first and then share with the question. Keep thinking of how to calculate that Poisson ratio and give me the ratio. Meanwhile, I take the question for solving. Document. This my file. Tutorial. Okay, let's do one calculation to appreciate how this calculation is done. Then you will have some imagination or understanding when I share this. Where's the good file? Where's the good file? It's here. Come on. And quickly go to. I want to solve at least 2 questions today, so that the third question you can do it yourself. Right. Can you see the screen? You are asked to calculate the strain developed in the members. You see the structure given. A load is here. Don't worry about, as I told you before, please forget for a while your load, moments, everything just put aside. Look into deformation status only, right? And then, although it is happening, now we have to calculate only the strain. The job and the point of interest is to calculate only the strain. You are given with this arrangement, okay? You are given with this arrangement, right? What is here? The pin. You can see my cursor moving. Yeah, I think you can see, right? This is pin, right? There is a member held by a pin at one side and two rods. Two rods are hanging this member, supporting this member, right? And these rods, cable, right? They call this as a cable. This is a cable, huh? Cable, cable 1, cable 2, right? And these two cables are firmed, fixed to the support here at this point and this point, this point and this point. Again, it's a kind of a pin only. At this point is pin, and although it is fastened into the wall, the joint is just pin. These are all the conditions. But the support and load is not much important right now, because you're going to just see the deformation or displacement or the deflection in simple word. Let me do the calculation quickly. Just one line answer only, right? Start with given data. Let's do the given data. You are given with load, load P. That is not much important anyway. Cables are there. You are all given two cables, right? What are the cables? BD and CE. BD and CE. Our point of interest is at BD and CE. BD and CE. And then there is a value 10 mm given, right? 10 mm. C is displaced because of this load. This C, at C, it is displaced or deformation is given. We denote the deformation in terms of, right, deformation, or what is I use the same word, displacement. Displacement at displacement. Please stop me if you not understand at any point. Displacement at C due to which member? CE. Due to CE is equal to 10 mm. It is given to you, okay? C is given to you, okay? And then normal, you are asked to required answer will be, is there anything else given? Don't worry about the load, just P is acting and is tend to elongate the member. You see the direction. And then required answer will be, required answer or solution is, required answer is, you are asked to find out the normal strain. The question itself says normal strain, meaning what? It may be either elongated or shortened. That is called normal strain due to normal stress acting on it. Required answer is normal strain produced at the cables, okay? At the cables BD and CE. Only one deformation is given, and you are asked to calculate deformation at both cables, the strain at both cables. Having given the change in length, you are asked to calculate the strain, the sigma, right? I denote this by sigma BD and sigma CE are asked. Come on, let's do this. Coming here, let's draw the free body diagram. Always the solution starts with free body diagram, otherwise we cannot understand what is happening, right? I split the video here. So when you draw the free body diagram for this member, for the given member, right, your free body diagram will look like this. You are given with, I start from the support, right? The support condition is like this, a pin joint, and there is a member, right? There is a member, and there are two cables, right? I use another color. There are two cables located, right? There are two cables located, right? Straight line, take it as straight line. Straight line. And then each one is pinned here again, pinned here, okay? And this end is called as A. And go back to A, B, C, B, D. This one is D, right? D, and this end is C. Okay, and then what else given to you? That's all. And there is a load acting. Mark this number. This is C, up to C only, right? This end is not there. This end is not there. Okay, and there is a load acting on it, P. Okay, when the load is acting on, initially it is a length, it is a length of, initially it is a length of, what is the length given? 4 mm or 4000, let it be 4000 mm, easy for calculation. 4 meter is given in the question, I changed to 4000. Initial length of this both BD and EC are 4000 mm initially, and then due to this loading the member will get extended, right? We are talking about this one, members, concentrate on this. Due to this loading, this will also bend, and this members also, the cable will also get extended. I use this color, okay, black. The cables will get extended, right? Eventually the member will also get deflected in this way, isn't it? Get deflected in this way, not to scale, not to scale. And the value of this deflection is given to you already. This is 10 mm, right, in the question, and this is not given. I take the new position of the member as C dash and this position as B dash. Okay, please keep this in mind. Okay, let's move on. This is our free body diagram. Have I mentioned everything there? Now you're asked to calculate what is the strain in these two members, BD and CE. BD and CE. Can you see the letters clearly? CE, the big one. I think I have given all. Now I denote this. I denote this deformation as delta. See, you can mention the strain as this one or this one. This is small delta. This is big delta. Big delta. Both are referring to deformation. Okay, the unit for deformation. Unit for deformation. I use the big one, which is delta. I call this as delta BD because it is occurring at BD for the member BD. I call this one as delta CE. The extension or elongation as delta CE. With that, you can calculate the other values. Okay, let's do this calculation. So remember these diagrams, everything, and then do one by one. For wire, the solution started. I do the free body diagram already. The solution started for wire or cable. CE, let me start with CE. For CE, we define by definition how you have to calculate the strain, right? The strain value at CE. What is the definition? What is the definition? Anybody? Tanchi? What's the definition of strain? Definition of strain, please, quickly.
Deformation.
Change in length to origin length. Upper change in length, I take it as BD. Change in length to original length BD. Both of them are given. Change in length at BD is given. We are talking about CE. I'm sorry. You correct me. I have too much imagination. I do something wrong. CE. Okay. Right. And then all the values are given, so I can conveniently substitute the values of CE. Change in length in CE, this is the change in length, right? C2 to C dash. C dash is a change in length which is 10 mm, right? That is my change in length. Original length is 4000 mm. 4000 mm. What is the answer? You will get, please check later because time is running. You can check, I'm sure you will get the same answer. This is the answer for your strain at, I got one answer, strain at CE. Now we have to get the another answer. This is one solution. Let's go on to the second cable BD, wire BD. Wire BD. For wire BD, you can calculate the strain, the same formula. You need the formula for BD is equal to change in length for BD over original length of the BD. Do you have all of them? Change in length? Don't have, right? This one, B dash. B dash is unknown. Is equal to B dash is unknown. And LBD, anybody can answer me? Do you have LBD? Original length of LBD is given or not in the question. See the diagram carefully. Answer me whether original length of BD is given in the diagram.
No.
Who said no? Please check carefully. Original length of
Yes.
BD
Yes,
is
miss.
Yes, yes.
required.
4000 mm.
Very good. It's already given. Let it be there. Now some of them known, some of them not known. To find the unknown, which is BB dash, to find BB dash, to find BB dash or otherwise, or I call this as a convenient for me to BD itself, BD. Come on, let's use the similar triangle principle. Upper similar triangle, I have one triangle like this, isn't it? One triangle is my A, this is C, this is C dash, this is one triangle. Okay, let's use the similar triangle principle. Mathematics helps you to solve this. There's another triangle, which is this one. I put inside like this. I put on inside blue color, which is B dash. I use the similar triangle principle here to calculate this one, right? By similar triangle principle, which is A C C dash and A B dash. Okay, A B dash. A, why I change the color? Clean this. I use red color. Red color is more fluorescent color, clear. Okay, between triangle ACC dash and ACC dash and ABB dash, I can solve like this. Okay, finish the question. Right, I can solve by this triangle, similar triangle principle. Okay, my similar triangle is here. Come on, let's write down the sides. Let me write down the sides. This should be equal to this, and this should be equal to this, isn't it? This should be double dash should be equal to this. I'm going to compare between these two sides, the similar sides. When they are similar triangles, similar sides also are in ratio. So let's write the ratio between these triangles so that we can find out the unknown, right? This is together, and the blue also come, although it has come down, just take it as together. Now let me write the equation. By similar triangle principle, I can write delta, start from the known value. Delta C, you know, right? The deflection, any delta C is equal to 10, right? I know already 10. So delta CE is produced by which length? This length AC, right? Delta CE by AC, length AC is equal to delta AD, delta BD, delta BD by AB. Okay, by similar triangle principle, I say delta CE, or otherwise you just compare this and this and this and this. Okay, I reverse it, easy for you. Delta CE over delta BD, and then AC over AB. Now write the answers. You know delta CE is 10 mm divided by delta BD, you don't know, delta BD unknown, question mark, equal to AC, you know, right? The length is given to you. What is the length given to you? This length is 2, this length is 2 or 3, 3, I think. 3, right? 3. This is 3 mm, 3 meter, 2 meter, 2 meter and 2 meter. So I can write the distances like this. This distance is totally 2 plus 2 and then 7, right? 7 meter. And this distance is 3 meter. So I compare this value. My AC is 7 over AB is 3. Now find out the unknown. Delta BD goes up. You end up with 10 times You solve this one, you will get the answer, right? Delta B goes this high, so 10, 3 over 7, correct? What is the answer? 10 times 3 over 7. What is the answer? 4.28 mm I'm getting. You can check later. Huh? So I got the change in length at BD by similar triangle principle. With that I can find the strain in wire. Okay, the strain, therefore strain in wire BD is equal to, strain is the by definition change in BD over change. You have to really understand where the deformation is and substitute the deformation accordingly. All right. Okay. Delta BD is, you know, 4 point, just now we calculated 4.28 divided by original is 4000 mm. Thus I end up with 0.00107 mm per mm. Okay, that's all. We found the strain values at both wires, right? This is at wire BD and this is at wire CE. Any question? I stop here for this question. Shall we move on to the next question? If you have no question on this, do you have any question here? I
No.
want to solve the next question. Huh? Anybody? No question. Right. Or shall I post the video? I already recorded that question. It's good we are working together, right? We should also move on with the classes. I ran for 10 minutes now. You can ask me question. If not, I will post the video. Please go through. If you still cannot understand, I will do it in the next class. Okay. I will now start the video for the second question, wherein there are some multiple loads. Here's only one load. The deformation is due to one load. Any question?
No, miss.
Okay, I start the next question. Let me unshare this. Second question. I'll share this one. If no question, I will move on to the next question. Why there is nothing shown here? What happened? Hmm. Why it is? Oh my! I mean tablet mode. Sorry. Okay, let's do this question. If not audible, you tell me. Okay, this is a pre-recorded one. It looks very big. Such a simple question you have, you may have to follow carefully to understand, right? Just 2-line answer for this one. You don't have to worry about. Okay, let's solve this one. Are you ready? Okay. Right? The force applied at handle of the rigid lever causes the lever to rotate clockwise. About a pin B, where's a pin hand? The pin B. There's a pin, that's why about a pin B. From here, to start from here is the pin. From about B, it is rotated at an angle 2 degree and 2 degree, making an angle 2 degree. Determine the average normal strain. Now we are going to do the strain. Last time is all about stress and conductivity. Now is the second factor that we learn, strain. How much the strain in each wire? The wires are unstretched when the lever is in horizontal position. Do you understand the question? You are given with this is a support, right? There is a wire and this is pin and there is a support, wire is hanging, and this is here another support at F, a wire is hanging, and there is a handle. Okay, all these things are at equilibrium condition when no load is applied at E, and as it is stable with the depth at AH as 200, depth at GC as 200, depth at FD as 300. No, sorry. GC and FD are 300 at equilibrium condition or no load is applied at E. When no load is applied at E, it maintains 300 and 300. This is the wire's length. They are flexible wires, okay, steel wires. When a load is applied at E, it will tend to stretch itself, elongate, okay, change in length. The position here is can move to this point. The position here can move to this point, It is a little bit lower down. So how much is the value we are going to find now? You are asked to find, you are given with these conditions, you are asked to find the strain values at each wire. What is the strain value? What is the change in length? What is the change in strain? Not change in length, not just change in length. What is the strain at this point? So there's delta. If I keep the value, because I want to use the same notation that I use in the class, it is the AH, right? Delta AH, small one. I use the small one, easy for me to write. Delta AH. This is delta GC. This is delta FD, right? So these are the change in length. Okay, let's find out one by one how this is going to vary and how we are going to analyze this member. Any question here? Right. Whether I can remove this one, okay. Given data, write down the given data. Given data. Please work along with me. Are you doing it? All are doing it. Given data, you are given with the members and the depth, original depths are given. Better you write down the original depths, otherwise you'll get confused. Given that, sorry, I have the charger finished. Okay, one moment. The original length is capital L. LAH will be 200. You might write it like this. 200. 300. Original length of FD will be 300 also. Okay. You can even put equal to 300 mm, same. Okay. That we must know. And what causes? There is an angle. There is no delta given, but angle is given. Now a simple conversion of angle can give you all the change in value, change in depth conveniently. Right. Let's convert this angle into radians. Or before we do this one, let us draw the diagram first. Okay. Diagram how this is changed. I do it here itself so that it is clear on this diagram itself. Okay, I'll tell you this spot. The member will change. There is a handle applied to force applied to the handle of will change the position from A D to AD dash and E dash. Okay, we are rotating actually. Let it be like this. So change to AD dash actually. You see the differences in the values. What is the angle of rotation given? It is about B. How much is the rotation? How much is the rotation about B? 2 degree, isn't it? Since degree is given, you need to convert to equivalent values. You must know the equivalence of the radians between the degrees and radians. If you convert, you can conveniently calculate it. Okay, 2 degree. The angle of rotation is given. I am marking this one, and then we can solve for the answer. Okay. AF, GF, and FD are important. In doing so, you need to find the original and change in length in the members given to this. Okay, right. Let's start from this one. Required answers. Strain, strain value. I mark the strain at this point. Strain at AH, strain at CG, and strain at DF. DF, yeah, DF. Motion You must know the variation between, and this is the one of the solution is the free body diagram. I have drawn in the diagram itself. Please make use of it. And then our original length is AD, change in length is A dash D dash, the change in position. This is the original position, original, this is changed position, okay, right. And then you should know the difference between, one moment, you should know the difference between, the relation between radians and, what is the relation between radians and degree? I think you should be knowing. What is the difference between radians and degree? Any idea? We know that pi radians equal to 180 degree. Okay, pi radians equal to 180 degree. Because we cannot substitute 2 degree as it is for calculating the values. It is possible by trigonometry, but let's change to radians. You are given a 2 degree, right? So I want to calculate changing. You will get in. So pi radians equal to 180 degree. How much will be the 2 degree? What is the answer here? Very good. 0.035 or 39. You keep it like this. Radians. This is the value, equivalent value. So I got the value in radians. How much is change in value at this point? Right. I stop here for the class today. Okay. I post this calculation as well as the video. Okay. All of you, please go through that. Are you hearing me?
Yes.
Uh, please go through the video as well as the calculation. I post both of them in the CN now. You please follow. If you cannot understand, then we continue in the next class. I explain the correct, questions that you were not, questions and clarification that you need. Any question for the whole class today? Do you understand?
Can you post in MS Team?
Yeah, boleh. Both I posted for video and CN. Calculation. Calculation I already prepared. Only thing the video I have to extract. Okay. I will do it now. In another, you check by 8 o'clock. I have to give attendance also. All right. Anything else? No question. I stop here now. If no question, you can leave.